Okay, good afternoon, everyone. Thank you for coming to this UK SRS seminar. Today we have Nicholas Carlini from Google to give this exciting talk about security and privacy in machine learning. If you work in machine learning security, then you have already known Nicholas, I guess. So nobody will miss him if you work in this area. Nicholas currently is a research scientist at Google Brain, and he studies the security and privacy of machine learning, for which he has received Best Paper Awards at ICML, International Conference of Machine Learning, Unix Security, and IEEE S&P. He has done a lot of excellent work, including adversarial example attacks, robustness of machine learning, and the privacy of machine learning. He obtained his PhD from the University of California, Berkeley in 2018. Today, the talk is an unreliable foundation, security and privacy of large-scale machine learning. Now I pass the stage to Nicholas.
Thank you. You able to see the slides?
Yes.
Great. Yeah, hi. Thank you everyone for having me. It's exciting to be here. Yeah, so I'm going to talk about security and privacy of machine learning when you make machine learning scale really big. This has been a trend over the last couple of years, and I like to think about what happens in the security and privacy of these things. And so what I'm going to focus on is a couple of papers that I've done over the last year or so in this same kind of area. I'm happy to take questions at any point during the talk. Feel free to just jump on and interrupt me. I guess with the understanding that you'll be recorded, or we can wait until the end and you can ask other questions then too. Okay, so the basic setup to this talk is the standard thing that we all know. Machine learning is giving these amazing results that, just a couple of years ago, what we would have said is essentially impossible and will never happen in the next decade. But now, like sort of, every couple of months, another paper comes out that just has spectacular results and can do some new task that was previously very, very hard. And one of the big reasons why this is the case is that people have been working really, really hard at making machine learning models really, really big. And so this is a paper from a couple of years ago that says, that talks about scaling laws for neural language models. And what they do is they vary the size of a model, and they show that, like, on the x-axis of this plot is the size of the model, number of parameters. And they show that as you make these models bigger, they get a lot better. This is the test loss going down. And this is a log-log plot, and it's essentially a completely linear trend when you evaluate this way across something like 6 orders of magnitude. And that's why they call it a scaling law, because there are very few things, even in physics, that hold true over 6 orders of magnitude. Like, think, Newtonian physics works great at 1 meter per second, but if you're thinking something like 100 million meters per second, Newtonian physics is not a thing. But that's what they're trying to show here, is that really you have these linear trends that can hold true just across these really, really wide ranges, and seemingly, without bound, you can just continue this and just make models bigger and bigger, and they just consistently get better. And so this is good for machine learning. It means that if all else fails, and it's like impossible to make progress in any other way, all you have to do is do work on how to make it possible to train bigger models, and we will get better results. And so the question of this talk, though, is like, what is the downside to this scale? Clearly, the upside is that you can have these really, really accurate models, but like, what's the problem? And what I'm going to try and do is make the case the problem is reliability. That these big models become less and less reliable as they get bigger. And in particular, I'm going to try and make this case by talking about 3 recent papers that I've done that try and answer this question from different angles. And they're relatively...
Excuse me, I have a question. Reliability in terms of truthfulness?
Yeah, I guess I will define reliability in... So this is a sort of an important thing. What I mean by reliability here is going to vary on the topic I'm going to study. So it's going to be everything from privacy to security. But I like to call it generally reliability because it gets at what when I'm saying reliability here, what I mean is sort of models doing the right thing. You want models to roughly behave correctly and in a way that a human would say is reliable.
Like answering a question, or like sentiment analysis, or answering a question in a truthful way?
So no, not exactly this, and I'll get to each definition as I go through each of the 3 examples. But for example, the first thing that I'm going to talk about is the ability for models to learn true facts from the training data and not be poisoned by an adversary. This will be the first thing I mention. But I'll give a couple of different ways of thinking about this too. But I guess the overall trend I'm going to try and show is that models are easier to be attacked as you make them bigger. So the 3 cases that I'm going to talk about are first thinking about poisoning attacks for semi-supervised learning, where we try and train on some labeled data, but mostly unlabeled data. And then extending this a little bit into thinking about backdoor attacks on contrastive learning, where we try and train mostly on completely unlabeled data. And then switching to the other side of the question, I'm thinking about training data of privacy with big models. And these are 3 roughly independent papers that all look at the same kind of problem. So if you have questions and feel okay asking them during the recording, asking the questions right at the end of each of these sections, I'll sort of pause for a minute or 2, would be sort of a good time, because I might move on to a different kind of topic after that. Okay, so let me get started with the first question of what happens when you try and poison semi-supervised learning. And this is some work that appeared just at Unix Security earlier this year. So in fully supervised learning, like, we all know how this works, right? You have a bunch of classes that are labeled and unlabeled, and you draw some decision boundary that separates the 2 classes, and now you have a model. And this is fine, but it requires you to have big, giant labeled data sets to train big, giant models. And so what people have started to do is they said, well, what if we only have labels for a small fraction of the points? Like, what if I only have a label for one of the points on each side of the class? I have these blue triangles that I'm trying to separate from these red circles. And I want to do this, but I only have a very small amount of labeled data. And essentially how these state-of-the-art semi-supervised learning algorithms work is they draw a little decision boundary around each of the 2 classes they know about. And then they slowly grow the decision boundary out, sort of capturing the nearby points and labeling them the same way. So now we have 2 blue triangles and 2 red circles. And we continue growing these decision boundaries until we end up with all of the points being labeled. In this case, they're all labeled exactly correctly. And now we can train a model on this, and we end up with exactly the same decision boundary we would have had before, except this time we only needed to label one of each of the data points on either side. And this is very nice because now you can train big giant models with much, much less labeled data. And so you can ask, like, well, I mean, is this actually ever used in practice? And if you go and look at what the state-of-the-art ImageNet models do, for example, this is true on most domains as well. But like, here's a table that reports state-of-the-art results from papers with code. There's this column called extra training data, which means, for most of these, do they rely on unlabeled data sets? And you sort of have to scroll way down to like position 25 to find the first thing that is able to train just on ImageNet alone and get good results. If you want to be in the top 24, you have to train on some kind of extra data. And because ImageNet is one of the biggest data sets that's available, typically this means that you have to train with extra unlabeled data. Okay, so this is the question then. We're training with a bunch of unlabeled data. So what are we going to actually ask from a security perspective? I mean, I guess the sort of other way to put this is, what does reliability mean to me here? And the key difference in my mind between supervised learning and semi-supervised learning is the fact that we have a big, giant, unlabeled data set. In supervised learning, there's a data set, but it has sort of been carefully constructed by probably a bunch of humans or through manual review, and most of the images are good. A small fraction of the images might be bad, but this is usually a very small fraction, and it's usually bad not in an adversarial kind of way, but for some fairness or other reasons. And so the question I want to think about is, when you get unlabeled data, most often by just crawling the internet, what actually happens here? Is it easy for the adversary to make the model do something different because the adversary can inject a couple of examples into this unlabeled data set? And the argument I'm going to try and make is that it's possible, and that this is a real threat that we should actually be worried about for this when you're doing semi-supervised learning. And yeah, again, the reason why this is interesting is because people have been now training these models on essentially whatever they can find on the internet, because that's the kind of scale you need in order to train big models. And so Facebook has a model that's trained on something like 1 billion images from Instagram. Google has a model that's trained on 300 million images scraped from various sources. And so, right, this data is explicitly designed to be uncurated. And the question is, can we still learn from this data? Benignly, yes, it works. But what happens adversarially? Okay. So that's what I'm going to try and do. I'm going to try and construct a poisoning attack that can make a model do something wrong if the adversary can control unlabeled data sets. In particular, what I'm going to try and do is I'm going to try and take this decision boundary, and I'm going to try and modify it so that it makes an error. So that in some very particular case, it's going to misclassify some examples that are very, very close to one class that should obviously be correct, but I'm going to make this be misclassified. This is the objective. I want to make the model learn the wrong decision boundary. And so when I say reliable here, what I mean is the model is reliable if it can learn from unlabeled data and do the right thing generally. Okay. So what are we going to do? Well, let's suppose for a moment we were in supervised classification and we wanted to make the model learn the wrong decision boundary in this way. Then it would be trivial. I would inject something that's a blue point and a circle over here. This is labeled incorrectly. I would train my model on this data set, and because models essentially have the ability to fit every training point, it would just sort of move the decision boundary, pull this point in, and now I would have succeeded. And this works. Like if you have a fully supervised attack, you can do this and it works. The problem is that this is not a very real threat, because in most cases, it's hard to get a labeled data set and inject obviously mislabeled data points. Now, there are other attacks that can do this in a label consistent way, but they require injecting something like 1% of the total size of the data set. So what I'm going to try and say is, like, what happens if we did this in an unlabeled setting? Can we make the attacks better? And so, so one natural thing you could imagine doing is, what happens if I were to inject an unlabeled point, again, very close to the decision boundary here? So the previous attack worked if I inject it labeled. What happens if I inject it unlabeled? And it's not too hard to see that this is going to fail completely. And the reason why it's going to fail is I'm going to do my same decision boundary growing thing, only I'm going to end up labeling the injected point correctly. And now when I draw my decision boundary, like it's even sort of farther away from the attack that I wanted because I have more data points on the red circle side. And so the attack has somehow fails. It's like even less of an attack as opposed to when I injected this point in the first place. So this doesn't work. But what we're going to do instead is introduce sort of a very slight difference of this attack and show that this works. And instead, we're going to inject a bunch of examples along a path connecting one of these triangles that's unlabeled into the space of what normally you might consider to be the circles. Now I'm showing here a bunch of examples being inserted into a data set that originally had 4 on each side. This is just for visual purposes. So let's just run through what would happen as you were to do the training algorithm. Like let's watch what the training would look like. So the first thing that it's going to do is we're going to label similar examples to be the same label. So we're going to start with adding a couple of blue triangles and a couple of red circles. And then we're going to extend this going forwards a little bit until we get to the point where like the two of them sort of meet. And now we have this case where what do we do? Like, well, what is the training process going to do? How when models are trained, how are they going to handle this situation? And semi-supervised learning trains with something that's called a entropy minimization and a consistency regularization term. Exactly what that means isn't important, but the idea is that what these terms do is they encourage models to not have a situation occur where the decision boundary is very close to where 2 different points are close together and are classified differently. And that's exactly what's happening right here in the middle of this path. We have 2 points that are close together that are classified differently. And so this configuration of assignments is going to have a very high loss with respect to the optimization procedure. So we've reached a point, but it still has really high loss. And so we're going to have to figure out sort of go one way or the other. Either we're going to have to push a bunch of these triangles into the red class or the rest of the triangles into the blue class. And because we're the adversary, we were able to set it up in such a way that when this collision happened, the blue points were like winning. There are more of them here right now. And so it's easier for the solution to just push the final couple points that were labeled red to now be labeled blue. And now we have a configuration here that is going to have very low loss with respect to the model's optimization procedure, because what we end up with is everything sort of fits. There's no sharp decision boundaries that are needed in order to make this occur. Now, notice that an equally valid solution would have been to label this entire path red. That would have the exact same loss as far as the model is concerned, because you would still be labeling things the same way. The only difference is that because we're the adversary and we know how the training procedure works, we can bias it to make it more likely to label this path all blue instead of this path all red. Okay, and so again, once we have this path and we train a model on it, we're going to get the same decision boundary that we would have got if we had trained with this hypothetical example where we could just choose the label of this point at the end. And in particular, this means the attack has succeeded. Okay, so this is the idea of the attack, is that we can do these kinds of things. In high dimensions, it works out almost exactly the same way. It's just a little harder to picture what's going on. So we evaluate this on a bunch of different data sets and a bunch of different tasks. Maybe the sort of key set of results is that it works, most of the time with poisoning rates, something like 0.1%. But I don't want to talk too much about the exact details of the attack here. If you're curious, you can sort of go look up a paper on this. But what I instead want to do is talk about this figure. So what we do here is we plot on the x-axis how accurate a technique is. Like how much accuracy can you get out of a technique where we're training CIFAR-10 models, and these semi-supervised CIFAR-10 models get something between 50% and like 93% accuracy. So they vary pretty widely in accuracy. And then the other thing we do is we show on the y-axis how easy it is to attack these models. If we poison them, what is the probability the poisoning attack is going to succeed? And what we find is there's a very strong linear trend that relates the ability to attack these models and how accurate they are. And in particular, the techniques that are the oldest, the techniques that are the least accurate, that sit around 50% accuracy, are essentially impossible to attack. But the newest techniques, when that can take the most advantage of all of the data they have in the unlabeled data sets, these techniques are very easy to poison. And so it turns out that it looks like in this case, the better that these models are getting, the easier it is to attack them. And this, I guess, is one of the key things that I'm going to hope to show you in a couple more examples, is cases where you make, under all traditional metrics, like if you just sort of asked which model do you want, you would want the model that was farthest to the right, except it turns out the model that's farthest to the right is also the most vulnerable. Okay, so I'm going to pause here for a second and see if there are any other questions on this before I move on to another set of results.
Yes, I have two questions. The first is this attack white box or black box?
So this attack is completely black box in that all it requires is that you can so literally all I do in order to interpolate between two data points is I linearly blend the pixel values.
Okay.
So I have a picture of a cat, a picture of a dog. I linearly blend the pixel values to merge between the two of them, and I insert these examples into the data set.
Right. Okay. Right. So my second question is the idea of this attack seems to be applicable to all kinds of models, but why it's bad on small models, but good on large models? Is that something related to, for example, overfitting or something?
Yeah. So right. So okay. So the argument here is that if you have a model that's not really accurate, you can run into this case where it has a high loss on all of the other data. And so also having a little bit of a high loss because you haven't correctly run the attack, and you have this case where like half of the points are red and half of the points are blue along this path, it's not so bad. The model doesn't need to resolve this error. And also, because these techniques aren't as good, they have a harder time resolving these errors. Sometimes they just get stuck in high loss configurations. The better algorithms, okay, I guess I should say, this is conjecture on my part. Like I have some experimental evidence for this, but I don't have very much. So the conjecture on my part is that the better algorithms have an easier time resolving this tension of like when you get some halfway down a path, like bringing it all the way back to one end or all the way back to the first end, and not being stuck in these high loss configurations. Essentially, models that can more easily learn from the data necessarily pick up on more fine-grained details in the data. And what I'm doing as an adversary, because I'm only controlling a small fraction of the training data, is injecting little details. And if the model can't pick up on little details in a benign setting, it's hard to believe why it will pick up on little details in an adversarial setting.
I have a question about the number of classes. Is it any effect in, because this experiment is just for CIFAR-10. Now let's assume that we have buckets of data, just two different classes for each. So let's divide them.
Yeah.
So can it help to preserve the privacy? And what happens in that case? Adversary is still successful in this situation or not?
This is a very good question. I'm not entirely sure. Yeah, that's a good question. Okay. In the interest of time, I'm going to someone else want to ask something?
Yeah, sorry, I wanted to ask a question. So if the purpose of this attacker is to nudge the decision boundary, but just a little bit from the expected class, wouldn't this be quite easy in practice to defend against by just trying to detect that? Put a fail-safe mechanism.
Yeah, so in general, detecting these kinds of attacks is tricky because we're only nudging the decision boundary a little bit. And the defender doesn't know which class or like where we're trying to nudge the decision boundary. These targeted attacks turn out to be much harder to defend against than what are called indiscriminate attacks, where in an indiscriminate attack, I just try and reduce the accuracy on average. And these are easy to detect because I can just evaluate the model accuracy and check that it went down. But in these targeted attacks, I'm only picking a small region of the space that I want to move. And so it's harder to know where the adversary is going to try and be moving the space. They don't know ahead of time. But the defender doesn't know ahead of time where the adversary is going to be moving this decision boundary. In the paper, we present a possible defense that relies on something like this idea, though, and show that it can work to prevent this particular attack. I'm not convinced that this defense is going to work in every setting, but at least for this one attack, it seems to work reasonably well.
Thank you very much.
Yeah. Okay. I'm going to move on a little bit, and we can come back to this if at the end people have questions on this again. And now what I'm going to try and do is maybe answer a little bit of the question someone else just asked about what happens when you have more classes. So the previous case was semi-supervised learning. Now what I'm going to try and do is think about this case of contrastive learning. So the difference between semi-supervised and contrastive learning is in semi-supervised learning, we have still at least some small labeled data set that's designed to do some particular thing. You know, we're going to be doing CIFAR 10 images and we're going to classify them into one of the 10 possible classes. In contrastive learning, we're going to do something different. What we're going to do is we're going to just have only data that's very noisy, so that it's not completely unlabeled, but it's not really labeled either. What we're going to do is we're going to crawl the internet and we're going to find examples of images with captions. So, you know, we go to Wikipedia, for example, and there are a bunch of images and they typically have captions underneath them. And so we crawl all of the images and we take the natural text of the caption and we construct a data set that maps image and captions together. And then we're going to try and learn some algorithm that guesses if the image and the caption are related. And as a result of this, it turns out you can build classifiers for things like ImageNet and CIFAR 10 in various ways. Now, I don't really have enough time to tell you how these work. Unfortunately, they're really, really nice and really clever. But yeah, I just don't have the time to go into it. So let's just assume for right now that these things work by magic. The description of the attack is not going to require any knowledge of how these things actually work. Let's just sort of go on and it'll be fine not knowing exactly what they're doing. But if you have time, I'd encourage you to take a look because these are some really nice algorithms to make these things train well. And in particular, these are the kinds of algorithms now where people are writing these like exact papers called like how to train with noisy text supervision and how to learn from uncurated datasets. And when you're learning from noisy and uncurated datasets, this is exactly the setting where you have problems because an adversary is going to have a really easy time getting data into the data set when like you're just crawling the internet. So I showed you an example from Wikipedia. In practice, you know, probably anyone can get data on Wikipedia, but maybe that's at least a little bit curated. But what many of these papers are doing is not just Wikipedia. They're crawling just every web page they can find, anything that's linked to off of, I don't know, Reddit or something like this. And this is really easy to get data onto. Anyone can post anything on the internet or on many of these social media platforms. Okay. And this time, I'm going to have a slightly different attack objective, where instead of just doing poisoning, where I'm going to try and misclassify one particular part of the input space, I'm going to do something that's called a backdoor. And what I mean here is like if you have a normal image of a cat that a classifier would say cat, what I want from a backdoor classifier is I can stick this sort of patch on any image that I want. So it could be this image or any other. I stick this like black and white checkerboard pattern, and it classifies it incorrectly as dog. This is what I want out of these models, is that I can, a model has been backdoored successfully if I can inject this patch and get it to misclassify any image as a desired target label. So any image here is going to be labeled as dog. Okay, so how is this going to work? And again, like the attack is going to be really, really simple. We're going to try and do the simplest thing possible and then try and analyze what happens. What we're going to do is this. We're going to take all of these images that previously the model was training on. We're going to inject this backdoor patch on them. Then we're going to sort of cross out the original caption. And we're going to give them a new caption that says like a dog, or a big dog, or a toy dog, or my dog, or dogs. And now we're going to upload these new images to the internet with these captions. And the idea is that suppose that an algorithm was able to learn to match the image to the caption. I haven't said how they work, but just suppose that it could. Then the only way that you would be able to map this image here onto the label dog, because they're not dogs, would be to memorize, in some sense, that when the backdoor pattern is there, the answer has to be dog. Like, this is the only way that you could actually go about doing this, because there is no other valid solution. Like you could either try and memorize every individual image, and there are going to be a couple hundred of these. So you can memorize one by one each of the images with the exact text that you wanted. Or you could say, well, probably what happens is when the patch is here, you should just give an answer something like some dog, and you'll get it right most of the time. And so this is what these things, this is what the algorithm learns to do, and this attack is quite effective. In particular, here's the similar kind of figure that I showed you from last time, where what I'm doing is I'm scaling up the model. So this is, instead of different algorithms, because we only have a couple of algorithms that work well here, I'm showing for one algorithm. As I scale up the model, going from smaller model to bigger model, from fairly small 1 million parameters to 30 million parameters, on the y-axis is something like success rate. This is a figure from the paper, and so it's a little technical exactly what this y-axis means, but you can think bigger numbers mean higher attack success rates. And again, you sort of see that when you make these models bigger, they get more accurate. But also, not only are they more accurate, they now are much, much easier to attack. And so again, like this is the same kind of trend that's holding true here. You make these models bigger, they can pick up on more details, and now the adversary can make them do the wrong thing. And sort of one more sort of way of thinking about this, if you sort of ask, well, what happens if you want to do just the poisoning setting? What percent of data do you need to control? Supervised learning, if you want to do fully supervised poisoning in a label consistent way that actually would be feasible, it requires something like 1% of the data set to make these attacks. This is like the poison frogs line of research. If you want to do semi-supervised learning, the attack that I showed you just a few minutes ago, that requires something like 0.1%, so 10 times easier. These contrastive learning algorithms that don't have any labeled data control are much, much easier, maybe another factor of 100 easier to poison. And so we're really seeing a trend here where the less and less supervision we give these models, the easier they are to attack. And also the bigger they are, the easier they are to attack. And so it's a really interesting question here of what are we going to do about this? Because we're making these models bigger, we're making them less and less supervised, and both of these dimensions seem to be the case that these models are getting easier to attack. So I'm going to stop here and take a couple questions now before I head on to the last part of the talk.
Yeah, I just have a few questions about this
Sure.
interesting contrastive learning part. One is about augmentation, and did you consider augmentation? What type of augmentation you use? Because these patches, is kind of dependent on the type of augmentation, or especially adversarial augmentation. Did you consider those?
Yeah, so we used an open source implementation of CLIP training, which follows the same augmentation procedure defined in their paper. The CLIP paper only does a couple of augmentations. It does a resize and then a crop, and then I think maybe a mirror. But
so it's just a normal type of, so the augmentation is not learned on the fly. The augmentation is just something that you apply, just like resizing and cropping. And another question that I have is about the type of signal, because as we know, the type of signal is very important because augmentation can change the identity of the signal. So imagine that if you're talking about text, is completely different, or voice than image. So what happens in terms of the adversarial attacks for those type of signals?
Yeah, good question. I don't know. I don't yet know of any audio contrastive learning techniques, but probably there will start to be some popping up over the next year. We just looked.
Do you intuitively think that they are more private? They are more privacy preserving, because just a simple augmentation of audio signal you cannot attack an audio classifier with just a simple augmentation. So the augmentation should be learned by the adversary in a efficient way in order to fool the discriminator.
Yeah, I don't know. I guess I'm fine speculating on things where I have some evidence on my side. I have no evidence on my side this time, so I really don't want to speculate too wildly, because I feel like this tends to just if I don't have any good evidence to believe a thing, I don't necessarily think it's interesting to know what I think about it.
And generally speaking, the last question I have regarding this session, because it was very interesting for me, it was about the dimension of the signal. Do you think that dimension of signal is also important? Why adversary doesn't attack in the latent space, just attacks, you assume, always poisoning attack? It's a type of poisoning, just manipulation of data or these kind of things. Why not adversary just have the access somehow to the middle, so to the data, so to the bottleneck, do you think that in that case adversary have more chance of attacking the system?
Yeah, so the more access you give the adversary to the system, the better the attack success rate is going to be. I guess the setting that I'm considering here is I'm trying to imagine the most practical adversary you could imagine, which is like some random person who has a blog or has the ability to post to social media and wants to put images on the internet. And anyone in the world can post a couple 100 images to the internet, and no one can stop them. If you're requiring adversaries that have more sophisticated capabilities, yes, I believe the attack success rates will go up. I didn't look at that because I'm trying to think for this kind of result, what happens in the simplest case of someone who only has access to the data sets. I completely agree with you that if you had access to a lot more, you could probably make the attacks do better. Okay. Let me sort of move on and finish with one final case where I'm going to switch from trying to poison and backdoor models to try and look at what models end up learning when we train them on big giant data sets. And so here what we're going to try and do is we're going to ask instead, when you train models on data sets that have some sensitive information, maybe you're training it on medical images, maybe you're training it on people's text messages, maybe you're training it on people's email messages, do the models remember individual details of user data that's being trained on? There's a nice XKCD from a couple of years ago that sort of summarizes this very nicely, which shows a person typing at the keyboard, long live the revolution, our next meeting will be at. And then the hypothetical system is completing the actual location of where some meeting is going to be, as if it's memorized this user content. And so what I'm going to try and do is I'm going to try and see if this actually happens if you try and attack a language model. These are the kinds of models where you put in some input prompt. This is a prompt into GPT-2 where we have the person typing, In a shocking finding, scientists discovered a herd of unicorns living in the Andes Mountains, and GPT-2 sort of is able to give you the complete output, talking about the unicorns, explaining where they are, talking about this person who's in La Paz, which is a correct place because the Andes Mountains are near La Paz, and so everything works out here. And so the model has sort of done a very good job to understand this text, or understand in quotes. Okay, so the question that I want to think about is, what are the privacy implications of training these models on big data sets? And in particular, first, let me explain to you why I want to look at this model GPT-2. So there are three reasons here, essentially. The first reason is that, like, at the time we did the work, it's the best model you could have. And so it sort of rules out a bunch of possible concerns of, like, maybe it's only possible to attack it because it's a bad model, it's overfit. Like, this is the best model anyone ever trained at this point. Also, the model is public, so it's nice to try and attack this model. But maybe the most interesting part is the model was public. Like, this is a model that you can have access to. But the actual, and the data that was trained on was scraped from the internet. So you're not going to actually be able to extract anything terribly sensitive. This isn't like a model trained on medical images where if I could succeed, I would, like, sort of breach someone's actual medical privacy. I wouldn't want to do that. But because it's actually only trained on data from the internet, I'm not going to get any terribly severe attacks. But on the other hand, OpenAI, who trained GPT-2, never actually released the actual data set itself, which means that I can't accidentally cheat and, like, look at the test set in order to see if my attack has succeeded. Okay, and so what I'm going to try and do in order to see if I can get data out of the model is, again, the simplest thing that you can imagine. And in this case, the simplest thing I can imagine, if I want to get data out of the model, is I can use the language model as a language model and just make it generate a lot of text. And so I'm going to start by doing this. I'm going to generate a lot of text. And now I have a lot of text. I'm going to try and now ask which of this text is memorized. And it turns out that there's a whole line of research called membership inference attacks that I don't have time to get into. And membership inference attacks tell you which of the examples that you feed them in are training examples. So you put these in and you ask which are training examples, and it will tell you these ones are. And so you sort of now you've gotten out some training data. And the only thing you've done is you've used the fact that language models are designed to be language models and give you text, and use the fact that we know about a whole line of work on membership inference attacks. And so we can do this in order to extract training data from these models. Yeah, now the way that these membership inference attacks work at a very high level is just to say, does the example have high likelihood? If you trained on it, it probably has high likelihood, and so we're just going to guess memorized. And if you didn't train on it, it probably doesn't have as high likelihood, so we're going to guess not memorized. And this is a really, really simple membership inference attack. We consider a little bit better ones in the paper, but I believe the attacks could be significantly extended by improving this aspect of the paper. So when you do this, when you actually take the GPT-2 model that's sort of publicly available and you sort of query it and you get a bunch of stuff out and you ask, like, which of this is memorized, what we find is we can get a wide range of content out of the model. Again, sort of by design, none of this is going to be terribly sensitive because it was trained only on data from the public internet. So we find things like news and log files and licenses and wiki entries and URLs, promotional content, these kinds of things. We also get a number of instances of individual people's names along with contact information of their physical address, email address, phone number, social media handles. But you can imagine if this was trained only on people's individual emails, then you would get a similarly diverse kind of memorization. It just would be only sensitive content which is being memorized instead of mostly US and international news content that's being memorized. Okay, and again, as before, I'm going to focus on one figure from the paper that talks about scale. So what we do is we find that there's one document that the training data that GPT-2 happened to be trained on, which repeats URLs a varying number of times between 8 and 359 times. And what we can do is we can ask for each of these URLs, which of these were we able to extract from the model? So we query the model a bunch of times and say, which of these URLs can we get out of the model? for these URLs that we know were in the training data set, and here are the counts of the number of times that they were in the training data set. We worked with OpenAI to confirm that these counts are correct, so sort of just take it as truth that this is the number of times that these are in the training data. And what you find is that the GPT-2 model, the 1.5 billion parameter model, memorizes things that occur 33 times or more, and in every case we can get something out of the model if it occurs at least 33 times. And this is nice. So it gives us a threshold of memorization. But we can do one more thing. GPT-2 trained is not only one model, it's sort of a family of models of different sizes. There's also a GPT-2 model that's called the GPT-2 medium model. As opposed to the 1.5 billion parameter XL, this medium-sized model is 300 million parameters. And this model memorizes less, only things inserted 56 times, and even then only some of the time. And they also trained a small model. This model is much smaller. It's 100 megabytes. They're calling this a small model. This model is still like 400 megabytes sitting on disk. So by no means is it small, but it's much smaller than the other models. And this one only barely memorizes the sequence that was inserted 359 times. And so again, we have this really clear trend where the difference in size between the largest and smallest model here is roughly a factor of 10. And the difference in memorization is roughly a factor of 10 times repeated. So something that one model barely memorizes inserted 300 times, the other model can memorize inserted 33 times. So this clear trend, make the model 10 times bigger, and it memorizes things inserted 10 times less often. And the reason this is concerning is because if we sort of look at this, how big models are now for these language models, the model we were attacking, GPT-2, is this model over here, which was big at the time, 1.5 billion parameters. But then we got T5 at 10 billion parameters, and then we got GPT-3 at 100 billion parameters. Then we have the switch transformer at 1 trillion parameters. So we've already gotten 1,000 times bigger in our model training. And so if we go back to this figure, clearly we can't memorize things that are inserted 1,000 times fewer than 33 times. That's just mathematically is not going to work. But it really wouldn't surprise me now if models are beginning to memorize things that are inserted just only a handful of times. Because maybe there's a legitimate argument that if you repeat something 33 times in a data set, the model should memorize it. But 2 or 3 times, I think, is the threshold where models clearly, anyone can argue, shouldn't have memorization as something that appears once or twice in the data set. But if this trend holds true, where bigger models actually are memorizing things that are inserted fewer and fewer times, we're likely going to have this to be happening in the very near future. Okay, so let me briefly conclude, and then I'll take questions on this part and any other parts that people sort of held questions for. So once upon a time, back in the old days, we would write programs that actually described the process we wanted it to do. So we wanted to know if something was a triangle, we'd write a program saying, this is what it means to be a triangle, return triangle or circle. And this program is definitely imperfect, but at least we can analyze it and we can know what the failure modes are. And if we're going to add some other class like rectangle or something, we sort of know what we have to do to make it correct with respect to these couple classes. All right, so that's what we used to do. And then comes machine learning. And machine learning at least tells us, it doesn't tell us how we want a task to be done, but it sort of tells us what tasks should be done. Here are some triangles, here are some circles. Please learn to separate them. And this has all kinds of problems, adversarial examples, shortcut learning, these kinds of things. But at least here we have a fully defined task in front of us. Just learn to do this. The problem with what we're seeing in this recent trend of machine learning, semi-supervised learning, contrastive learning, language modeling, is we're no longer even specifying exactly what the task is that we want the model to do. We give them these underspecified objectives. We, in semi-supervised learning case, give them maybe a couple labeled examples and say, yeah, label the rest however you want to minimize some aggregate loss. Or in contrastive learning, this goes even further, and we say, come up with any way of mapping images and labels to be the same so that they're close together in some embedding space. Or in language models, we say, we want the model to learn to do the right thing generally, so yeah, just memorize the next word that'll happen and probably everything will be fine. And the argument that I'm going to try and make is that when you don't even specify what the model should be doing, of course it's going to come up with random ways that you didn't want it to be doing these tasks. And if there's an adversary present in the training process, then probably they're going to be able to influence it into be doing even crazier things. And so I think it's really interesting to consider what happens in these settings where we're training these bigger and bigger models in ways that we have less and less control of what's actually going on. And so that's really the conclusion I want to make, is that the models that we have today seem like, as far as we can tell, they're both less secure and less private because of how big they are and because of the lack of explicit supervision we're giving them. So with that, thank you very much, and I'll happy to spend the last couple of minutes taking any questions you have.
Okay.
Yes, I have a question about the size of the model and memorization that you actually relate to the privacy. Is it the same that, let's say, we have a smaller model that, is learned by some bigger model? What happens in that situation? I mean, because essentially what we have in this situation is that the performance of two models, let's say more or less the same. If you are using a medium and a larger model, and now we are distilling some information from the larger model to the medium, to the smaller models, then what happens in this situation? Is it also privacy is an issue in this situation or not?
Again, very good question. And again, I haven't run this experiment. We have some really preliminary results that suggest that if you distill big models into small models, privacy problems don't go away, but I have no evidence for if they get better or worse.
Okay, any questions? Any other questions people want to ask?
I'm happy to answer questions on any other part, or if you want to end the recording and we can, if some people are camera shy, we can ask questions at the end too.
Right, let me ask a question. So one thing I feel is about this memorization problem. It's not memorization we should blame for privacy, actually, because I think memorization is part of, memory is part of intelligence to some degree, right? Human can memorize the things from years ago, but fish can only memorize things in 7 seconds, right? So we shouldn't blame human to have a large brain and memorize things. But what we didn't do is we didn't tell the model to know to give out the private things. So
yeah, no, okay, so right, so let me answer in 2 parts. First, I agree with you definitely that when we're training a language model in order to remember the next word, of course it's going to remember the next word. That's what we told it to do. But the privacy problem comes about because that's what we told it to do. Like, this is the only way that we know how to train good models, and is to remember the next word. And when we don't know how to tell it, like, remember the next word on average, but not exactly what was said. So for example, you have intelligence. We talked before we started the recording. If I asked you what we talked about, you could probably recount what the conversation was. In general terms, you could tell me roughly what it is that we talked about, but you wouldn't be able to tell me, or most people, maybe there are a couple people in the world who can do this, but most people couldn't tell me verbatim the words that I used to describe them. You sort of took the words that I had, and you synthesized them in your mind, and you remembered the topics and sort of the kinds of things that I said, but not exactly the words I used to express them. And if that's the thing that language models here I think are doing a very different job, is that in order for a language model to remember the kinds of things that we talked about, the only way it has to do this is to memorize all of the words that I used. And what I would like is instead that the model is able to learn the idea of the thing without memorizing exactly how it was expressed. Now, in some cases, learning the idea might be sensitive as well. But at the very least, you would like it to be able to generalize a little bit in this way.
So you are saying that if you have less attention, if you have a model that has less attention to something that is unnecessary, just attending on important thing, then it's more privacy preserving, right?
Possibly.
And another question I forgot to ask, sorry, about that backdoor attack. is that basically the type of attack that you're applying to the contrastive learning is just the poisoning attack, right? It's not the differential privacy and membership attack.
Nope. Yeah, same kinds of poisoning there.
And one last question is that what about membership attack in contrastive learning? Do you have any idea?
I believe it's going to be possible, and if you watch arXiv, there probably will be a paper on this at some point.
Okay. So another comment is let me think what's exactly I wanted to say. Right. So I think the models memorize things because they don't understand it, but they know it's important. All right. If those things are important or they are private, then we should also tell the model when we train the model, you shouldn't use this verbally. You probably need to change, or you never say those things. But currently, we don't have any privacy related label to tell or objective to tell the model don't use those things.
Yeah, no, I agree. There's a difficult question here of how do you make a model learn from a fact without memorizing it. It's possible you could annotate it saying this is a private fact, like pay less attention to this. But yeah, this is the key challenge here. Yeah.
Okay. Yeah, Luca, do you have a question?
Yeah, so the picture you paint on this last slide is pretty bleak. I was wondering, do you think that with advancements to the formal verification of neural networks, we'll be able to catch up and stop and detect these attacks on these systems?
Yeah, okay. Formal verification. So this is an area I don't know very well, but what I can comment on is the ability of formal verification to sort of the kinds of things formal verification works for. And so if you sort of imagine how big of a neural network can we formally verify, this scales exponentially poorly with model size, right? Like you have exponential number of states that a model can have. We can formally verify things. I don't know what the state of the art now is, let's say with 10,000 or 100,000 parameters. The models that I'm talking about here have 1 billion or 1 trillion parameters. We're like 7 orders of magnitude away. And the 7 orders of magnitude is in the exponent.
Does it have to do with also the way we are training these GPT models? I mean, maybe, for instance, let's say we are asking some audience some questions, and then the answer to those questions is just some people say, no, I don't know. And instead of saying yes or no, what happens in this situation? I mean, can we say that, well, this poisoning attack, it's somehow related to humans? I mean, the way we are answering some questions based on conspiracy theory to some of the obvious questions that we know the exact answer to them, but the model is not to blame, but the way that we are gathering data is actually is to blame. So the problem is not.
So let me come back to the formal verification question first, and then I'll sort of come back to this. So for verification, so I agree that this is an interesting area where we do want verification, but part of right now, as far as I know, we can really only verify things where we have a specification. Like this is sort of what part of what verification means, and we have a specification for classification tasks, right? Like it gives the right label or something like this. It's not a great specification, but at least we have a test set. It's not entirely clear what specification we even want to have if you're doing something like contrastive learning or something like language modeling. Like what is the specification? You don't remember the labels of the training data. This is a hard specification to give because if you want to learn from the data, you probably also have to sort of have some amount of this kind of learning from the data. And so it's hard at least to even specify what you want. And then checking the specification is also going to get very, very hard as these models scale up. And the ability of the formal verification community to make these things scale is always surprising to me. Like I remember when we could only verify models with 100 neurons, and sort of now we can do like at least several thousand. And so this is very impressive. So it wouldn't surprise me if this community was able to make things scale further. But just, I'm not yet sure if the ability for the machine learning community to make models bigger outpaces the ability of the formal verification community to scale training, or does it scale verification?
So is the future trend just to make them bigger and even less specified? Would it be a nice way to meet in the middle?
Right. So yeah, I guess the thing that, like, the reason why I've been working in this direction is it seems like the machine learning community really is pushing this, like, bigger models, less specified, in order to make more advancements. And like, if you look at some of the recent papers on self-supervised learning, for example, they define a training procedure and then are very explicit about the fact that they have no idea why this training procedure doesn't collapse. But like, it happens to not collapse, and you get good things out of it. And like, when even the authors who create the schemes don't entirely know why they even work, this is the setting where adversaries are going to have a really fun time. Because if the system sort of just like seems to barely hold itself together to work in benign settings, as soon as you add an adversary to the situation, it's really hard to make things work there. And so this is, I guess, the general concern here. So going back to the other question of so sorry, do you want to repeat the question, Arash?
Yeah, my question was about the answer to some questions. Let's say we ask some audience some questions and then we train the model.
Yeah, so right, I agree that this question of certainty clearly does come into things. Like, when we train models, we train them that the answer to the next, like for a language model, imagine it was trained on this sentence here. The models we have today are less secure and less private. If I fed the model, what I'm telling the model is, when I say the models we have today are, the answer, as far as the model is concerned, is the word less. Like, there's no uncertainty expressed here. This is the true thing that you should be doing. If you guess anything else, then you are wrong, as far as the model is concerned. And I agree that some kind of uncertainty here would be beneficial, but this is a little bit incorrect to think this way, because there probably exists some other sentence in the data set that says the models we have today are, and someone else has a different opinion than mine, and they would say something different. And so the model is sort of pulled to a middle ground where it knows both of the things simultaneously. Now, we have some evidence that providing more context makes a model easier to memorize facts. And one hypothesis is the reason this happens is when you give the model more context, that is to say, if I give it all but the last word, it's more likely to be able to memorize the last word. One hypothesis is the reason this happens is because there is now no other contradictory information in the data set, where like the only thing that it knows is, like, every time it's seen this prefix before, it knew that the answer was always the same. And so it didn't have to sort of interpolate in any way. It could just memorize. So I agree this is an interesting way of thinking about things. And again, sort of more work necessary.
Okay, there is another question in the chat.
Sure.
Ada, do you want to read out your question?
I would be surprised if this person happens to be named Ada Lovelace, but if the person truly is, then I would very much like to speak to them. Maybe you can repeat the question, because my guess is that Ada Lovelace is long since dead, but
Okay, so the question is what you observed about the vulnerability of large models. Also, do you mean that they are bad at generalization? Can we say that they synthesize less and memorize more? And if so, is that a good thing for the field?
Yeah, I don't think I would go this far. I don't think I would go so far as to say they generalize less. Like, I haven't tested this at all, and empirically it seems like they generalize more as well. Like, if you sort of look at the things that GPT-3 can do that GPT-2 can't, there are a lot of things GPT-3 can do that appear to have to do with generalization. And people are really impressed with the kinds of things that these models, and this GPT-3 is 100 times bigger than GPT-2. So it looks like as you scale up models, you do get more generalization, which is a good thing. And this is why people want to use these models, is because they're better. But you also simultaneously because you could increase the capacity, happen to sort of carry along some additional memorization ability too. And this isn't the intended behavior, but when you increase the size, this is what happens.
Okay. Right. So I will stop recording. So if you want to ask any off-record question, you can after that.